I want to talk about this program called MonumentAI. Monument. I downloaded it from MonumentAI. I clicked this button up here, Get Monument, chose the basic plan, went through this process, went through payment, and it was a pretty straightforward process. Downloaded it, got an email, told me a registration code, and I clicked the installer. As soon as I had done that, I opened the window, and this is what you see. Get some pretty straightforward full screen developer tools, help, website, about. This looks like a save file, open file. This, I think, is a toggle for the menu. And this is the forecasting button. So I went ahead and built this test file. And you can see this right here. It's a pretty straightforward test file. Very straightforward file format. And I figured this out by looking at some of the test examples that came in MonumentAI toolkit test data. I'll show you that in a second. But column A is always the date. And here are my dates. I've got some data sets in here. Some of them have data points all the way to the back. Some of them to the beginning of the time series. Some of them start a little later. There are some zeros in here. There's some missing data. I've tried to make this a fairly realistic representation of a file that one might see in finance and in the wild. Once you build this, I put this on the desktop. Input, so you load that file. Here's on the desktop. I'm going to open that file right here. Click open, and it tries apparently to convert it. It tells me what these values are, and that looks about right. I've got one column for dates, and the rest here are numbers. I go ahead and click OK. And this GUI is pretty straightforward. It's not that complicated. Dimensions. So I figured out you have to drag and drop that date over here. And I've built a couple of different curves here. I've got a sine curve. Looks something like that. I've got a denser version of a sine curve that's pulled more frequently. Looks something like that. I've got a broken up sine curve. So here's a sine curve that has zeros in the middle. I've built a broken null sine curve with a gap. A sawtooth. It's a pretty popular one for volatility modeling. I've added a sawtooth onto a sine curve. This is what you typically get. This might start to look like something like VIX. I've got a sine, which is a higher frequency sine added to a lower frequency sine. This is a classic example of the time series that will break a lot of models for time series prediction. Here's sine on a trend. So the higher frequency sine added to the lower frequency sine added to a trend. In financial modeling, that would be known as a linear trend. And then finally, I've added the sine, the sawtooth, and the linear trend to get a waveform that is almost certainly not predictable by a out-of-the-box AI algorithm. To explore the GUI a little bit more, I noticed that if I drag a couple of these on at the same time, it will go ahead and show them superimposed on each other. I can turn these on and off like this. I can look at one at a time, two at a time, etc. And so it's a pretty straightforward graphing tool. And I noticed that I've got a couple of these models here. And so if I want to predict this dense, let's see, this sawtooth added to a sine, which would be this red line. So I might drag this to the end, so it's at the end. And here I'm going to drag this algorithm called entropy boost. And entropy boost has a number of options. I can configure those parameters down here. I can do the same thing up here and add the parameters. Up here, I also have another example where I can turn on and off some of these other time series. So in this case, this entropy booster allows me to select the, it's projecting the saw sign, so I can't turn that off, but I can go ahead and project it with or without these other time series. So here's what it looks like if I just use the projection on the sawtooth plus sine. Here it is if I go ahead and add in sine and the dents again, and we'll notice that the projection up here updates, gets a little bit more accurate. I can zoom in to this projection here. So if I zoom in, this is where my time series ends, and here is the algorithm projecting a number of time series forward. How many it forecasts forward is a parameter I get to set. Look back period is how much it's trained on. Look ahead period is over here. I could change this to 15 and see how well it does forecasting 15 points up. And the short answer is it starts to get a little wavy. I could go ahead and add a couple of other time series to this and see if I could smooth that out. In this case, I added the sawtooth, so I can go ahead and visualize that by dragging that on here as well. So here's that sawtooth that's been added, that red one right here. So this can start to get to be an eye test if you get too many of these, but you can see that adding this straighten this out a little bit. So that's entropy boost. So let me clean that up a little bit. So I'll take that off. I'll turn this off, and I still want to focus on this saw sign. But let's see how I can do just with that. Let's take some of this other data, and we'll pretend like we're using, try to predict this one forward. This is the sine plus the sawtooth on a line, or a trend. This AR is autoregression. This is probably the most common out-of-the-box quant modeling toolkit. Windowing period could be 50. I could switch that to be something like 30. Click that, just like that. And you'll notice that that will update that projection very quickly. I've got different windowing methods. You can do rolling, expanding, shuffling. Rolling is a window that moves over time this way. Expanding starts at 0 or starts at the point, and always just advances, but always from 0 forward. Expanding might emulate a back test. Refresh rate, look back period, look ahead period. So I'll go ahead and change that to try to stretch that algorithm even further. And here you see it's memorizing, or it's extracting some pattern. I'll zoom in. That's what it thinks it is. And so that's autoregression. The DLM, dynamic linear model, based on Kalman filters. So I can go ahead and click that open just by clicking that and go to the description. I can set the parameters initially before I drag it on. I can then drag it on. As I drag it on, it highlights this sine saw line to tell me that that's what it's going to try to predict. Now, if I zoom in to that, I can see that the Kalman is trying to predict 5. Let me go ahead and change that. Parameters, look ahead period. I'll change that to also be 15. Click that over, and that'll update. So that 15 is projecting down. So that DLM is clearly going down, whereas that autoregression is wanting to follow that trend. I think it's almost emulating that. That's going up. Look ahead 15. Let's see what those do. Now, a look ahead of 15 is probably stretching both of these algorithms beyond what they're intended to do. But if I were trading this sine saw line curve as if it were volatility, I would probably use an AR. If I were trading it a little bit more like a stock, I'd probably be looking at the DLM. I don't like the look of that DLM, so I'm going to go ahead and drag that off. This is a GDI-BM, Gaussian Dynamic Booster. Let's see how that does. In this case, it's following the autoregression pretty closely. Look ahead period, I can go ahead and bump that up to 15 and see how that might have expected. And what we'll see is that both of these algorithms are projecting the same thing might happen. P1 is prediction 1, P5 up to P8, P9. Let's say, so P9, thereabouts, both these algorithms project the same thing. And we only start to see a deviation starting around P11, P10, P11. Based on my experience, I would say the Gaussian dynamic booster Boltzmann machine is a higher quality projection than autoregression. The LSTM is the typical out-of-the-box algorithm. I'll bring that into play with some of these basic sine curves. But let's see what the entropy booster would look like. So the entropy booster is green, and the entropy booster is the one that will incorporate more than just a single time series into its projection. So here we have these 2 time series versus this one. Now, what I can do in this tool is I can say, okay, the sine saw line probably will be benefited by the incorporation of that sawtooth variable, likely also the dense sine line, which is brought in there, and probably even the sine curve. So if I bring all of these in, I can go ahead and take that entropy booster, which is now purple, and I can update it to take advantage of these 3 additional series into its projections. So I can add this, and add this. Click OK. And now that entropy booster is taking advantage of these 3 additional time series, in addition to just intrinsically learning on the previous sine saw line intrinsic value, like the autoregression and the Gaussian dynamic booster. So the entropy booster is taking additional information from these 3 other time series into its projection to arrive at a more accurate projection. And you'll see it's what it's figured out is there's sort of a pointy line, a curvy line, a curvy, a pointy, curvy. So it's trying to get a point back on there. So it's seeing that it's going point, curve, point, curve. It tends to be pointy, curvy, pointy, curvy. And so it's looking for that pattern. And it's getting that probably from the combination of this and the intrinsic. If I go back to this, I can't set these other algorithms that I've added to have other multiple independence. I could use Gaussian booster as well. I could see how that does. That gives me a very different kind of line, make sure that the independents are right. I could go ahead and deprive this one of the various data sets to see if the intrinsic only projection is any better. But let me do a side-by-side comparison of the entropy booster that has all of these 3 independents, plus an entropy booster that we deprive of those independents, and we will turn those off. And just like that, I can do a visual inspection to see that the entropy booster here, the first one, which is purple, versus the second one, which is now pink, the inclusion of the additional data smooths that line out on the projection and generally drives it higher. That tells me intuitively that there's something about the patterns that it's detecting from these 3 additional time series that is causing that entropy booster to want to drive those values higher. So it would tell me that the data that I've selected, if I exclude it, I'll get a lower value. If I include it, I get a higher value. That's an intuition that I wouldn't normally get if I was just doing this modeling in Python. I can slide this window around to see where these predictions start, or I can zoom back out and see the whole time series. And just like that, in a very short period of time, I have gained an intuition about the addition or subtraction of multiple types of training set data into an algorithm that is today considered as at the top of its class, and that is entropy boosting. So let me reset this very quickly. Let's see, I could add some of those as independent time series, but I won't for this example. I'll take these off and bring this just back to the dense. Let's see, just a simple dense line, and train in LSTM. So this is a classic out-of-the-box AI, machine learning, data science type analysis. And LSTM takes quite a few back propagations, iterations to run. This is standard and expected for LSTM. Despite the fact that it's been around for a while, it is still, I find, in finance, especially in quant finance, one of the more frequently used models for large data sets, and it does run for quite a while. It takes some compute processing to run. Here it's running natively, locally on this laptop. And we'll see how it does. It'll do okay. And this is an incredible demonstration of how long some of these algorithms take versus the LSTM. LSTM standing for long short-term memory network. There are a lot of data points here, and that's why you're seeing this take this much time with the standard projection parameters. I could have changed the parameters, and I'll show you that in a second before running it. So here's the projection. It's about to finish, and we'll see how it does. And we can see it's not great. So what we'll do here is we'll change the parameters, and we'll say the batch size may be a little bit smaller. The look back period we'll set to be smaller. Windowing we'll do even smaller, and the look ahead period will we'll do only 3 points forward. And then we'll drag this next version ahead, and this one will run a little bit faster on us, in part because it's not calculating as many windows. The windows are smaller, and we could have set the iteration count to be lower. This second LSTM that we're running will have less information and less look back than the first one that we've put together. So let's see how starving this time series of data helps or hurts. Almost done. And we'll update shortly. So here we go. We've got, with less data, it's learning this sequence. With more data and more iteration, it's looking like that. Now, what we can do up here is we can show the error rate. So the first one gets down to about -7, and the second one gets down to about -10. So actually, for some reasons, the second one is training better. Okay, so all that compute time was placed in here just to calculate a sine curve, and it's this is generally getting the trend, but this is not great on this this analysis. So what we could do is we could go over here and let's see what the Gaussian dynamic Boltzmann machine looks like. Okay, this one it's looking like it needs more complexity, more data. So let's just run the entropy booster, and here we go. That was almost instantaneous. That entropy booster has figured out this trend and is generally going to go up. We could probably even push that a little further and really try to stretch that algorithm. So that's 30 points. Let's see if the entropy booster has learned the shape of this sine curve. Does it ever go down? And sure enough, yes, it does. So it's going to go forward, and then it's even going to go down. So this is learned that quickly. I wonder if the Gaussian booster will also look. So let's see, look ahead with the 50, and we'll stick the Gaussian booster up here. Sure enough, it also has learned very quickly. So these two algorithms down here, these models, are more advanced than the ones, these out-of-the-box traditional prediction models up here. And I know that the number of models in this list will grow as this MonumentAI adds more. Basic point here is that some of these models and the booster-based models are quite fast compared to the traditional ones. This is the light GBM-based model. So for those that know what level 2, I think this is level 2 normalization, followed by a light GBM-like algorithm. And if we look into how that does, it does okay. It's got this projection going up. Let's set the parameter to be a little bit further, see how that does. Let's see, that's look ahead period, so maybe that's too much. So it's updated, and as we go in here, we can turn this off, and sure enough, the light GBM model with level 2 normalization does in fact go up. So not as smoothly as the entropy booster. So you can see that the entropy booster is outperforming light GBM in terms of replicating that initial time series. So we have a direct comparison of the benefits of boosters over LSTMs for sinusoid-like sequences. And what we could do is we can take we'll take these LSTMs off because they don't seem to be doing too well for us. And we'll take off these entropy boosters and the light GBM and take off dense and see if the performance is any better with entropy boosting on this. So entropy boosting is doing okay here, but what we notice here is that it's decayed pretty quickly here. It's got some idea that there's a recurring pattern here, but it's missing the sign on sign. So let's add something like a baseline sign, and then add this into the model and see how the tool does if we feed that into it. So what we'll see is that if we take this second sign normalized without that trend, and we fed that as well to the entropy booster, it's already doing better. The next thing to know is that this we can just take the lower frequency line, which is that dense line, and see if we can add that into the model as well. Here we're adding dense, and so here we would expect a little bit of an improvement going up. Probably if we had added a basic trend line to it, it would have done even better. Just for fun, let's see if the sawtooth on top of that sign line, if that forcing this model to accept that as well, see if that helps or hurts. So in this case, forcing this model to incorporate this jagged line in the prediction of this sign line is hurting the algorithm. That's not a good addition, and so we can take that sawtooth off and just see how the sign only lines help. Finally, we can go back and without adding it to the graphic, we can force the other sign. That obviously doesn't work. So we can turn this on, off, and very quickly get an intuition for which of these data sets is helping or hurting us. Let's take off this this dense. So we're dealing with a pretty challenging line, but still we're showing that entropy boosting is doing okay. Gaussian boosting, on the other hand, seems to outperform entropy boosting on this example. And here we can check Gaussian boosting is using the dense, the saw sign, and sign. Let's take off that saw sign, and we'll notice that it's, in this case, it is helping to get that sawtooth. Maybe let's add the other sawtooth, see how it does. In this case, the Gaussian booster does better with more data. The entropy booster is underperforms the Gaussian booster in this case. So this is a a very quick illustration of what can be done with this tool. I went from a simple test file, which I will share, using a densely polled sine curve, a loosely polled sine curve, broken, etc., and very quickly was able to show what those look like with various AI models. And then I was also able to get some intuition on which of these AI models and which of these data sets help or hurt. And I can also see the data, see the quality of the data, see the difference in the types of data that are being incorporated. In fact, I can drag these all on and just make a total eye chart here, and then use all of these just as a comedic endpoint here. Sine, saw line, and I will stick this into the Gaussian booster. And if I take all those data points and try to project 50 points into the future, let's do something absurd. This is something you would never do in AI. There you go, 100 points forward, and it's clearly, that is clearly too much for it. It's using all the data. Maybe we should turn off some of this. Take off these brokens. We don't need this. Sine, saw line. Maybe best that. And it shows you that if you are trying to predict too far, there is such a thing as trying to go too far with your projection. Let's go back to parameters and maybe set that. Something like 10 or 15 is already a stretch for an algorithm. If you were to download something like boosting out of the box from one of the GitHub tech toolkits, you would likely see an algorithm that would be tuned to project maybe 1, 2, or 3 points, but typically one next point. What you're seeing in this tool is Monument is already doing the work for you of projecting the shape of that curve out as many steps as we select here, which is just by changing this simple look ahead period, we are doing in a single value what would normally take a significant number of lines of code or steps to project. And obviously there's some tuning that's required in this. This is a very quick illustration of what this tool can do. I've been pretty impressed at the GUI. It's quite simple, it's quite fast. It makes AI very quick to use, and even just while we're here, I'm playing around and dragging and dropping different algorithms and testing which of these outperforms the other, which is something I can do without any lines of code whatsoever.